Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 32nd lecture of the course Discrete-time Markov chains and Poisson processes. So in the last couple of lectures we learned about this conditional arrival time distributions, and we also saw a few problems using that concept. So today we will start with we will continue with few more properties of Poisson processes. So let us start. So before starting with this theorem, let's recall something. So we saw that if Nt is a Poisson process with rate lambda, and if you can classify each arriving event into two types, say type 1 and type 2, further suppose that each arriving event or each event is type 1 with probability p and type 2 with probability 1 minus p independent of everything else, then if we count the number of type 1 events and count the number of type 2 events, then again these two are independent Poisson processes with rate lambda p and lambda times 1 minus p respectively, right. So basically if you split a Poisson process, then again those two processes again remains Poisson processes with different rates, and also they are independent, fine. So today we will see kind of an opposite result, like what happens if you merge or superpose two Poisson processes, right. So let's start. Let N1 and N2 be two independent Poisson processes with rates lambda 1 and lambda 2 respectively. So N1 and N2 are two independent Poisson processes with rates lambda 1 and lambda 2 respectively, fine. Now for t greater than or equal to 0, define this Nt as N1t plus N2t. So we are adding these two independent Poisson processes, fine, or we are combining the arrivals from these two independent Poisson processes N1 and N2. Then this combined process N dot is again a Poisson process, but now the rate just gets added up. So the new rate or the rate of the combined process is rate of process 1 plus rate of process 2. So lambda is equal to lambda 1 plus lambda 2. So you see this is just kind of the opposite result which we saw last like few lectures back, like if you split a Poisson process then it remains a Poisson process. Now here we are saying that if you superpose or add two Poisson processes, then again the resultant is a Poisson process. There the rates decreased, so it was from lambda it became lambda p and lambda times 1 minus p respectively. Here the rate increase because we are adding two processes, and the new rate lambda is lambda 1 plus lambda 2. So we see, so like the result which we saw some lectures back and this result, these are kind of complementary to each other, right. So if you add two independent Poisson processes, by adding I just simply mean and you define this new process Nt equal to N1t plus N2t, then this new process N is again a Poisson process with rate lambda 1 plus lambda 2, fine, okay. Next we have one more theorem about independent Poisson processes or two independent Poisson processes. Let N1 dot and N2 dot be two independent Poisson processes with rates lambda 1 and lambda 2 respectively. So the same setting as the previous theorem. then the probability that exactly n events of the process n1 dot happens before the mth event of the process n2 dot is given by this quantity. So, you have two independent Poisson processes n1 and n2. The previous theorem told you, like if you combine these two processes and look at the count the combined arrivals, then that is again a Poisson process with rate lambda 1 plus lambda 2. Now, this theorem is talking about something else. It is saying, okay, what is the probability that there will be exactly n arrivals of the first process before the mth arrival of the second process, right? So, like in particular, you can ask, okay, what is the probability that there will be two arrivals of the first process before the first arrival of the second process? Like this kind of questions, again, very real life questions, and today we will see some examples, then you'll figure out like how this kind of questions are very natural to ask. And now the answer is provided by this theorem. It says that the answer is given by this quantity, that the probability that exactly n events of the process or n1 happens before the mth event of the process n2 is given by this, where n is greater than or equal to 0 and m is strictly greater than 0. Fine, is given by this expression. Fine, okay. Now let us see the proof of this. So, the first theorem we are not going to see a proof of. Let us see a proof of this theorem. Now, by properties of exponential distribution, each event that occurs is an event of the n1 dot process with probability this, and it's an event of the second process or n2 process with probability this. Now, how are we getting this? Now, see. Now, once an arrival happens, the process restarts, right? Because both the individual processes n1 and n2 are Poisson processes, and also the previous theorem told us, like if we look at the combined arrivals, like both arrival from process 1 and process 2, that is again a Poisson process. So, once an arrival happens, say it doesn't matter what arrival it is, say of process 1 or process 2, then you can think for the combined process, you can think that it restarts itself. Why? Because we know Poisson process has this Markov property that it restarts itself, probabilistically restarts itself at every point of time, and the main reason for that is that the inter-arrival times have exponential distribution. So, suppose the first arrival is from process n1. Now, from here on, again you can think of that everything restarts. Now, whether the second arrival will be n2 or n1. How do you know that? Now, remember, n1 has inter-arrival times which is exponential lambda 1, because it's a Poisson process with rate lambda 1. So, this is for n1 process, and for n2 it is exp lambda 2. Now, n1 or the next arrival will be n1 if this exponential is smaller than this exponential. So, let me write this. So, next arrival will be of n1 dot if exp lambda 1 is smaller than exp lambda 2, and the other it will be from n2 if exp lambda 2 is smaller than exp lambda 1, correct? So, first arrival, may suppose assume that it is n1. Now this point on, once an arrival happens, the process restarts itself. Now the next arrival will be n2 or n1 depending on whether this. So remember, n1 corresponds to exp lambda 1, n2 corresponds to exp lambda 2, because these are the inter-arrival times. Now the next arrival will be n1 if exp lambda 1 is less than exp lambda 2, and the next arrival will be n2 if exp lambda 2 is smaller than exp lambda 1. Now we have seen this property of exponential distributions. So suppose if you have two exponential distributions, then one will be the minimum among the two. That probability is given by the rate of that particular exponential distribution divided by the sum of the rates. That's how you get that each event that occurs is an event of n1 dot process with probability this, because for n1 the rate is lambda 1, so the probability that exponential lambda 1 will be minimum among exponential lambda 2 and among exponential lambda 1 and exponential lambda 2 is given by this quantity, and an event of n2, that's when exponential lambda 2 is minimum of exponential lambda 1 and exponential lambda 2, and that probability is given by this. And why like this is true for each event? Because once an arrival happens, you can forget everything else and you can think that you are starting afresh, and that is because of Markov property of Poisson procession, which in turn comes from the fact that the inter-arrival times are exponentially distributed, and exponential distribution has this memoryless property. Fine. So the important thing is each arrival will be an arrival from process 1 with this probability, and arrival from process 2 with this probability, and this is independent of all that has happened previously by the Markov property or memoryless property. Fine. Thus for the required event, so what you want, let us see what we want. We want that probability that exactly n events of the process n1 happens before the mth event of the process n2 dot is given by this. Now, so the probability that there will be exactly n events of type 1 before the mth event of type 2 is given by, so if that has to happen, then among the first n plus m minus 1 events, here when I say first n plus m minus 1 events, I am looking at the combined arrival process both from process 1 and process 2, or in other words we are looking at the process nt, which is n1t plus n2t. Fine, which we know from the previous theorem is again a Poisson process with rate lambda 1 plus lambda 2. Fine. So for the required event to happen among the first n plus m minus 1 events, and again let me repeat here, I am looking at the combined arrival process, or I am looking at the sum of n1 plus n2, there should be n events of the process n1 dot and m minus 1 events of process n2 dot. So if I am looking at the first n plus m minus 1 events, so if there is any there should be n events of process n1 dot and m minus 1 events of process n2 dot. So if there is any less than m minus 1 events of process n2 dot, then there will be more arrivals from process 1. So again, this part is easy to see, that if the required event needs to happen, that exactly n events of process 1 before the mth event of process 2, then if you are looking at the first n plus m minus 1 events, there should be n events of process n1 and m minus 1 events of the process n2, and the last event or the m plus nth event should be from process n2. So the first n plus m minus 1 events, there should be n from, there should be n from n1 and m minus 1 from n2, right? And the last one, the last event should be from n2. Then only you will have exactly n events before the n events from first process before the mth event from process 2, because see, if the last event has to be from process 2, because if the mth event was before, then that means there will be less number of arrivals before the mth event. So the last event should be the mth event, and before that there will be n plus m minus 1 events. Among that, n events should be from process 1 and m minus 1 events should be from process n2. Fine. Okay. Now, what is the probability of such a thing happening? See, in the first n plus m minus 1, you need that n events should be from process n1 and m minus 1 events should be from process n2. Now, for that, what you need to do? You just simply need to choose. So, like in the first n plus m minus 1, which places or which events will be from process n1. Now, from n plus m minus 1, number of ways you can choose n places is this many ways. N plus m minus 1, choose n ways. So, in the first n plus m minus 1, among the first n plus m minus 1 events, there should be n events from process n1. So, you just choose from n plus m minus 1 places, the places for events from process 1. That can be done in n plus m minus 1 ways. And what is the probability of event from process n1? That probability is lambda 1 times lambda 1 plus lambda 2, and that should happen n times. So, that probability is n. Now, from process 2, the number of events should be n plus m minus 1, correct? Sorry, it should be m minus 1. So, in the first n plus m minus 1, there should be n from type 1 and m minus 1 from type 2, or from n1 and n2. But now the last event, or the m plus nth event, should be of process n2. Again, that probability is just lambda 2 over lambda 1 plus lambda 2. So, what you get is, so another, so this thing will get multiplied and you get lambda 1 divided by lambda 1 plus lambda 2 whole to the power m. Fine. So, again let me repeat, how am I arriving at this quantity? So, in the first n plus m minus 1 events, there should be n events of the process n plus n1 and m minus 1 events of the process n2. So, how can you choose n places from n plus m minus 1 places? That is precisely in these many ways. Fine. Now, that is how many ways such a thing can happen. Now, let us find out the probability of such events. So, that there should be n events of process n1, and you see an event is from of process n1 with this probability. So, you get this quantity lambda 1 over lambda 1 plus lambda 2 to the power n, and m minus 1 events should be of n2, whose probability is this. So, you get m minus 1, but now the last event again should be of process 2. That probability is lambda 1 over lambda 1 plus lambda 2. So, when you combine these two, you don't need this m minus 1 term, and you just get lambda 1 over lambda 1 plus lambda 2 whole to the power n times lambda 2 over lambda 1 plus lambda 2 whole to the power m, and that is precisely this quantity. Fine. So, the main thing that we are using here is this first line, that by properties of exponential distribution, each event that occurs is an event of n1 process with probability this, and an event of n2 process with probability lambda 2 over lambda 1 plus lambda 2. And then we just simply count how many ways the required event is possible, and the required event means among the first n plus m minus 1 events, there has to be n events of process n1 and m minus 1 events of process 2. Fine. That probability is n plus m minus 1, choose n, times lambda 1 over lambda 1 plus lambda 2 whole to the power n, times lambda 2 over lambda 1 plus lambda 2 whole to the power m minus 1, and then finally the last event, the n plus mth event, should be from process n2, and that probability is n2 lambda 2 over lambda 1 plus lambda 2, and hence we get the final result, right? So that's the proof of the theorem, and now we are going to see some applications of these two theorems. Fine. Okay. Now the first example, this will be an application of the previous two theorems that we just learned. So cyclones arrive according to a Poisson process with rate 8 per year. That in 10 years 8 cyclones come, so that's the rate. Earthquakes arrive according to a Poisson process with rate 5 per 10 years. So here the unit is per 10 years, right? So again, I have always said this thing that you should be careful about the unit, time unit. Further, assume that the arrival of cyclones is independent of arrival of earthquakes. So you see, this is precisely the setup of the two theorems that we saw in today's lecture, that you have two independent Poisson processes. So here one process is arrival of cyclones and the other process is arrival of earthquakes. They are independent of one another. Fine. Now what are the questions? First question is, find the probability that there will be no disaster in a given span of 5 years, and disaster means either a cyclone or a earthquake. So now we are looking at the combined process, right? So a disaster can be either a cyclone or an earthquake for the given problem. So the question is, find the probability that there will be no disaster, that means there will be no cyclone, no earthquake in a given span of 5 years. We know that this arrival of disaster is again a Poisson process with the combined rate. And the second question is, find the probability that there will be exactly 2 cyclones before the next earthquake. So for part B, we will need to use theorem 2 that we saw in today's class. So let us solve it step by step. So let n1t count the number of cyclones up to time t, and n2t count the number of earthquakes up to time t. Now it is given that both of them are Poisson processes. Now define nt to be n1t plus n2t. So I am looking at the combined process, or the process of arrival of disaster, which can be either a cyclone or an earthquake. Now then n dot is a Poisson process with rate 8 by 10 plus 5 by 10, which is 13 by 10 per year. So initially it was given in per 10 years, so I have just converted it to per year. That's why I have divided by 10 here, divided by 10 here. So the combined process, which I defined by n, is again a Poisson process with rate 13 by 10 per year. So disaster arrive according to a Poisson process with rate 13 by 10 per year, and here disaster means either a cyclone or an earthquake, right? And now what you are asked? You are asked the probability that there will be no disaster in a given span of 5 years. So we know Poisson process has this property of stationary increment. So the number of events in an interval just depends on the span of, or the length of that interval. So here the span is 5 years. So you just need to find out what is the probability that in a span of 5 years there will be no event from the combined process, right? So the probability that there will be no disaster in a given span of 5 years is e to the power minus lambda t, right? That is basically what is the probability that a Poisson process with parameter lambda t has 0 events, where lambda is given by 13 over 10 and t is 5. T is 5 because you are looking at a span of 5 years, and lambda is 13 by 10, which we have already calculated. So the probability that there will be no disaster in a given span of 5 years is e to the power minus 13 by 10 times 5, which is just e to the power minus 13 by 2. Fine. So once you can mathematically formulate the problem, solving is very easy, is just one line. Fine. And now what about this second question, the probability that there will be exactly 2 cyclones before the next earthquake? So Here in terms of theorem 2, n is equal to 2 and m is equal to 1. So that gives you this answer. So the probability that there will be exactly 2 cyclones before the next earthquake is given by this. Why? That is because, so again, I have just in this formula, my n is equal to 2, my m is equal to 1, my lambda 1 is 8 over 10 and my lambda 2 is 5 over 10. Fine. So when I plug in all these values in this formula, I just get 8 by 13 whole square times 5 by 13. Fine. And hence we get the answer. So you see, again, once we have formulated everything mathematically, finding the answers is very, very trivial because of the 2 theorems that we have learned in the beginning of today's lecture. Fine. So we see a nice application of the 2 theorems via this example. And you see, again, the example talks about some very real life phenomena like arrival of earthquakes, disaster, cyclones. All these are very real life things, and you are always interested in predicting how many such disasters you will have in a given span or in future. So again, these are very real life questions which you can easily answer if you can properly mathematically model them. Fine. Okay. So now moving on to the second example. So this example is not just particularly for what we learned in today's class, but it will use all kinds of properties that we have learned till now. So it will not just use the 2 theorems which we have learned in today's lecture, but all the theorems that we have, or all the properties of Poisson processes that we have learned till now. So starting from 7 a.m., buses arrive at a bus stop according to a Poisson process with rate lambda per hour. So there is a bus stop, and starting from 7 a.m., buses arrive at that particular bus stop according to a Poisson process with rate lambda per hour. Again, starting from the same time, 7 a.m., passengers arrive according to an independent Poisson process with rate mu per hour. So again, you see here the setup is very similar to what we saw in the 2 theorems that we saw in today's lecture. So you have 2 independent Poisson processes. So here, what are the processes? One is arrival of buses, which happens according to a Poisson process with rate lambda, and the other one is arrival of passengers, which happens according to an independent Poisson process with rate mu per hour. Fine. Now, when a bus arrives, all waiting passengers instantly board the bus and the bus leaves, and subsequent passengers wait for the next bus. So once a bus arrives, all the waiting passengers instantly board that bus and the bus leaves, and the passengers who come after that will wait for the next bus. Fine. So the situation is very simple. Again, a very real life situation. Fine. Now there are again 2 questions. Find the probability mass function of the number of passengers who board an incoming bus. So here the number of passengers who board an incoming bus, because this is number of passengers, so it will be a discrete random variable. So we can talk about its probability mass function. So the first question that is being asked is find the probability mass function of the number of passengers who board an incoming bus. So here, which bus, whether it is the first bus, second bus, is not important, again because of Markov property of Poisson processes, because once a bus arrives, passenger boards and the bus leaves. So you can think of then from that point onward, again the process restarts. So once a bus arrives and leaves, the process restarts. Fine. So all these things are like, will have the same distribution. So the number of people boarding a particular bus will have the same distribution because of this Markov property of Poisson processes. Fine. Okay, so find the probability mass function of the number of passengers who board an incoming bus. That's the first question. Now the second question is, given that a bus arrives at 8:30 a.m. and no bus arrives between 8:30 to 9 a.m., find the probability mass function of the number of passengers who board the next bus. Next bus means the first bus which comes after 8:30 a.m. So here the situation is slightly different. You are given slightly more information. The first one is number of PMF of the number of passengers who board an incoming bus. But the second one is saying, suppose you are told that at 8:30 a.m. a bus arrives. So again, from 8:30 a.m. onwards, you can think that the process restarts. So you can basically think of 8:30 as time 0. But now you are told something more. You are told that, okay, from 8:30 to 9, no bus arrives. So you are given this extra information, and under this information, you are asked the conditional. So here basically you are given, the probability mass function that you are going to find will be a conditional probability mass function, because you are given this information that the number of, that there has been no buses has arrived between 8:30 a.m. to 9 a.m. and some bus will arrive after 9. So the question is, how many passengers will board that particular bus? So 8:30 a.m. there was an arrival. Between 8:30 to 9, no arrivals. That information is given to you, and you are asked what is the probability mass function of the number of passengers who will board the bus which comes after 9, because 8:31 bus came, 8:30 to 9 no bus came. So after that some bus will come. How many passengers will board that bus? You are being asked about that. Fine. Okay, again let's try to solve the problem step by step. Let X be the number of passengers who board an incoming bus. Fine. So again, there are, in this problem also, there are two independent Poisson processes. One is arrival of bus which has rate lambda per hour, and another is arrival of passengers which is Poisson with rate mu per hour. Fine. Now n passengers will board a bus if there are exactly n arrivals of passengers before arrival of the bus. So say this is time 0. Now a passenger arrives here, here, and now suppose a bus arrives here. So the chance that this bus will be boarded by n passengers if there are n arrivals in this period. So n passengers will board a bus if there are exactly n arrivals of passengers before arrival of the bus. Fine. So now what is the question? You have two independent Poisson processes. One is arrival of passengers, which is Poisson with rate mu per hour, and you have arrival of buses, which is Poisson with rate lambda per hour, and you are asked what is the probability that there will be exactly n events of the process of arrival of passengers before the first event of arrival of bus, right? And now you know we have found out this general formula, right? We have found out this general formula. So in this case, n is n and m is 1. So if you plug in that formula, you get this, right? So this is for n arrivals of passengers, and this is for the arrival of the bus, right? So the probability that n passengers will board a bus, that is exactly when there are n arrivals of passengers before the arrival of the bus, and that probability is given by this quantity by the second theorem that we learned in today's class. Fine. So and this is for all n. So this is for n equal to 0, 1, 2 and so on, because this is number of passengers. So these are the values which x can take, 0, 1, 2 and so on, and the probability mass function, probability x equal to n, is given by this for n equal to 0, 1, 2 and so on. But the main thing here is that we are again looking at two independent Poisson processes, and we are interested in that there will be exactly n arrivals of one process before the first arrival of the other process, and we know a general formula for this, and we just plug in the values that we are given for this given problem, right? So you see, again, once we can write it down and analyze the given problem mathematically, then writing down the answer is very, very simple. Fine. Now for part B, Now part B is slightly different. So suppose this is 8:30, so which is the starting time. Now you are told up to 9 there are no arrivals. So some bus will arrive here and you want the total number of arrivals in this interval. Now again you see we can break this interval into two. So this is one interval 8:30 to 9 and the another interval is 9 to this. So when the bus arrives, so this point we don't know, this is a random quantity. So this is an interval where you are told that no bus arrives, and then the other interval is from 9 to the arrival of the next bus, right? So for part B, the number of passengers who arrive between 8:30 to 9 a.m. has Poisson mu by 2 distribution. Why? Because arrival of passengers is Poisson with rate mu per hour and we are looking at a 30-minute duration. So since the unit is hour, so 30 minute is 1 by 2. So we are looking at 30 minutes. So that is basically equal to half because the rate is given. So because the hourly rate is given or the time unit that you are given is hour, so 30 minutes is 1 by 2. Fine. So that's why you get Poisson mu 2 because it's Poisson mu t. Here t is half and mu is the rate of arrival of passengers. So this many. So again the number of people who will arrive between 8:30 to 9, that's a random variable and its distribution is Poisson mu by 2 distribution. Fine. But now again, so up to this there has been no arrival, but now again you can think of that the clock starts from here. Again, because interarrival times are exponential, you know from here to here there has been no arrival, but you can forget that because of memoryless property of exponential distribution. So or which in turn gives rise to Markov property of Poisson processes. So you can think that the arrival processes restart from 9 a.m. So you can think of that the clock starts from this point. But now then thus from 9 a.m. the number of passengers who arrive until the arrival of the next bus has the probability mass function as in A, because you can now think of 9 a.m. as beginning of time and then basically the number of passengers who arrive or who board the next bus. You are thinking from 9 a.m. as the starting time. So the number of passengers who arrive until the arrival of the next bus, and that PMA we have already found out here. So if X is the number of passengers who board an incoming bus, this is starting from time 0, like from one bus to another bus. So that we have already found out. So here because of Markov property or memoryless property, we can think that everything starts from 9 a.m. and then the number of passengers who arrive until the arrival of the next bus has probability mass function as in part A. So now if Y denotes the number of passengers who board the bus, then what will be its PMF? So Y basically is the number of arrivals in this interval and the number of arrivals in this interval, right? So if I call this as so number of people who arrive between 8:30 and 9 as x1 and then 9 until the arrival of next bus as x2, then probability y equal to n is just simply sum over k running from 0 to n probability x1 equal to k and x2 is equal to n minus k. So if the combined has to be n, then in one of these intervals there has to be k arrivals and in the other interval there has to be n minus k arrivals. Only then, because the total number of arrivals is arrival from 8:30 to 9 plus number of arrivals from 9:30 until the arrival of the next bus. So again these two are independent. Why? Because of memoryless property or Markov property. So the number of passengers who arrive between 8:30 to 9 and 9 onwards, because we are looking at Poisson processes, so we know it has this property of what is called independent increments. So we are looking at disjoint intervals. So the arrivals or the events happening in disjoint arrivals are independent. So this x1 and x2 are independent, right? So this joint probability will just simply be probability x1 equal to k times probability x2 is equal to n minus k, right? And that is what this quantity is. So this is k running from 0 to n. This part is the probability that x1 equal to k, or the number of arrivals from 8:30 to 9 is equal to k, that is Poisson with parameter mu by 2. So a Poisson distribution is equal, the random variable distributed according to Poisson distribution, its value will be k. That probability is 1 over k factorial e to the power minus mu by 2 times mu by 2 to the power k, and then this is what we are getting from part A, that there will be n minus k arrivals before the arrival of the next bus, that is given by mu over lambda plus mu whole to the power n minus k times lambda plus mu. So this we get from part A, right? This is the probability that starting from time 0 there will be n minus k arrivals before the arrival of the first bus, or the probability that there will be n minus k arrivals of passengers before the arrival of the first bus. That probability is given by this. Now this is just because of the property of Poisson distribution, and these two are independent, again because of the property of Poisson distribution, because we are looking at disjoint intervals. And so the probability that y equal to n, if y denotes the number of passengers who will board the next bus, then it's y will be basically x1 plus x2, where x1 is the number of arrivals between 8:30 to 9 and x2 is the number of arrivals from 9 until the arrival of the next bus. These two are independent. So probability y equal to n is just sum over k running from 0 to n. So k from one part, n minus k from the other part. So k and k can vary from 0 to n. So k running from 0 to n, probability x1 equal to k intersection x2 equal to n minus k, but because these are independent, probability of the intersection is just simply product of the probabilities, and we get this formula. Fine. So probability y equal to n is given by this quantity, where the first part is because of Poisson distribution and the second part we get from part A. Fine. Okay. So you see, again we have used the two theorems that we have learnt in today's class, plus some additional properties of Poisson processes that we have already learned in previous classes. Fine. So again you see we have solved two problems which talks about some very realistic real life, or very realistic problems, or very real life problems we have solved, but the main challenge was formulating those real life problems mathematically, formulating them in terms of two independent Poisson processes, and then the questions that were asked were very, very simple applications of the properties that we have learned till now. Fine. Okay. So we'll stop here today. Thank you all.